and we thank Rob once again. And at this point in proceedings, it gives me great pleasure, obviously, to invite David Cox to give his reflections on either today or 41 years ago or anything in between, and indeed the future. Yes, please.
Can I be heard? Well, I have a lot of people to thank. Those who've put such a splendid effort into organizing today's meeting, the speakers, and now I'm arguing retrospectively, and that always has dangers to it. The referees to the paper I've already thanked. In between them, though, colleagues and students who worked on topics associated with this, and particularly David Oakes, with whom I wrote a book, very recently, it's only, 30 years ago. And when we were working on that, David was on the 4th floor of this building, so this building has played some considerable part in all this. Then going back to the paper, the referees were kind. Reading a paper to the RSS in those days, and probably still, is a quite hazardous business because people can be, of course, always very kind, but also quite merciless in their criticism. And I did have uneasy feelings about parts of the paper, although I think, in fact, there's nothing seriously wrong with it. But then, most importantly, the people whose questions led to the paper, and my memory is not very good these days, so I may have missed somebody very important, in which case I apologize. But they included Peter Armitage, who also at that time was here in school, and Marvin Zellen, who was probably at that point at Harvard, and Ed Gehan, who was at the MD Anderson Center in Houston, Texas. And all three of them were saying the same thing, that they were faced with analyzing censored survival data with the possibility of multiple dependencies, and they wanted to do it in a way that was intellectually secure and didn't depend on very strong assumptions. They were all saying basically the same thing. And this would have been about 1967, perhaps a bit earlier even. And their immediate reaction, all three, was they didn't want to touch exponential distributions, which would have been, in a way, the obvious route to proceed, a basic exponential distribution, and then with the mean modified or in some way or other. So I suggested the Weibel distribution, and which I think was a good suggestion, and one which probably I would think as came up earlier today. I think it was a useful one. It's good both because it's, the Weibel distribution function is easily handled in terms of likelihoods, but also it's got this intellectual backing in terms of extreme value theory, Armitage and Dahl, and of course from an engineering perspective, Weibel himself was a Swedish engineer who had introduced a distribution in the 1930s in terms of strength of materials. And in fact, it had appeared in a paper by Fisher and Tippett in 1925, which was based on strengths of materials in the textile industry. So there was a physical model basis to this. And it perhaps helps understand the paper a bit, to me at least, to all, that at that time my interests were primarily in stochastic processes and industrial statistics, because 1970, the period immediately after the Second World War up to round about 1970, intellectually, much of the new work in statistics was coming from manufacturing industry. Not business, but manufacturing industry. Britain was a great manufacturing country. And medical statistics, of course, was always important, and in particular the work of the school was always important back over a much longer period. But medical statistics wasn't as predominant as it is now in terms of putting forward new ideas into the subject. Meetings of the Biometric Society in those days, which were big meetings, important, but with a pretty strong, still with a pretty strong agricultural slant to them. So back to these people who kept suggesting this problem. So they didn't like the Weibull distribution. The fact that I was interested in stochastic processes meant that one thought of survival or end of survival as a transition, and in stochastic processes things are described by transition probabilities, and the hazard is a transition probability, and that's why I think my first formulation excuse me, my first formulation of the issue was in terms of the hazard, in formulating the probability of a transition taking place. So round about 1960, having exponential distributions and Weibull distributions dismissed, the next thing was the non-parametric proportional hazards. And so I suppose that was about 1968. And then there's the little issue of how you analyze the data from it. And although it's totally obvious how you analyze the data from it, it took me about 3 years at least to see that it was totally obvious. Or maybe not so totally. But if you look at it the right way, it is really. And so then Ed Guillen very kindly provided an example, which is really, as he pointed out, totally inappropriate, but nevertheless it served to illustrate the method perfectly well. And so that's how the paper arose. Now, that's the past. The emphasis very strongly was on isolating the effect of different explanatory variables. And it was on estimating and not testing hypotheses about. That was in line with what I think was the general view in theoretical statistics at that time, that estimation was important and the tests were tests of significance are important, but are in danger of being overemphasized. So that's why the emphasis was on estimation. And it wasn't on the hazard. The underlying baseline hazard was a nuisance. I think it was called a nuisance in the paper. That's not to say, obviously, that other problems, including this issue that we've just heard about a few moments ago, which is essentially about what do you do about individual patients, the issue that keeps arising, in fact, a friend and I had an email only yesterday from a clinician saying how important it was to be able to describe conclusions that would help the individual clinician faced with an individual patient, and that to tell the patient that a randomized trial, however immaculate, had established so-and-so was not immediately convincing for the individual patient. Intellectually, in one sense, maybe. And of course, much of what Dr. Henderson was saying was really about that issue of the individuality. If one was making predictions about groups of patients, the situation would be much clearer. But any prediction of a binary response pretty well is bound to have a rather poor sensitivity. And now, while we're on Professor Henderson, I should take him up on his... we're talking about retrospective memory. His retrospective memory of this incident with his motorcycle is extremely misleading. He forgot to tell you a common room of people almost going down on bended knee. Don't do it, they said. He's dangerous. Don't go anywhere near him. And they don't tell you either that when we got to the destination, he pretended not to know where he was and made two 363-degree turns at very high speed. Now, this was a long time ago. I've forgotten how many years. I'm not going to go as far as to say it was before causality had been invented, which isn't quite true. But the issue is, why was he doing this? Because he's such a nice chap, really. And I think I know the cause. This was in Newcastle. Newcastle's a long way from Manchester. And incautiously, earlier in the day, I'd made a semi-flippant remark about Manchester United. And Manchester United, you see he's nodding, Manchester United supporters are a relentless lot. They're utterly unforgiving, and so this was how he got his own back. Now, of the things that were around then, some were the precursor of more recent developments. There was quite a lot of interest in point processes, and that really naturally led into the current interest in systems of point events rather than single events of survival. And there was the notion, for example, of a modulated renewal process, it was called, where you took one of the standard stochastic models of point events and imposed an external explanatory variable on it. And this is illustrating the danger of this retrospective recall business. You're all far too young to encounter this very severe hazard. But it is that when you look back, you think, but we knew all that years ago. And of course the point is we didn't know all that. We knew, we might have known, I mean, when I say we, I don't mean I personally, I mean informed statisticians of the time knew this and this and this and this. There's a danger of, because we knew some things about mediation and causality, certainly things like that, to assume we knew much more than we did. That's a hazard that one runs. To some extent, remember that the interest was on the form of the dependence. And one of the points I'd like to make is that while it was important to have methods that would check for the adequacy of whatever it was, form one assumed, and that was partly why the use of time-dependent explanatory variables was an important part of the paper, so that these things could be tested. In many contexts, they're not that important because of the following. And this is something that I first came across through Sheila Bird's thesis, Aberdeen thesis, where she'd analysed a set of data 2 different ways and got, of course, 2 different ways, 2 sets of different regression coefficients. But these regression coefficients were almost exactly proportional to one another. So that for 2 variables, x2 and x1, beta 2 over beta 1, while beta 2 and beta 1 numerically totally different in the 2 analyses, the ratio is almost exactly constant. And there is a theoretical explanation of that. There's also a sort of empirical, well, a more qualitative explanation that the ratio of 2 regression coefficients is how much do I have to change x1 to produce the same effect as a unit change of x2. And to some extent, that's relatively independent of how you measure the response. Or a bit more technically, you could transform the response by some way that's more or less linear. That ratio, that relative slope will remain the same. And as I said, there are theoretical results about that. But that's partly why, if you're interested in the relative importance of different explanatory variables, in some respects, the choice of the proportional or not, for instance, isn't very critical. Sarah Darby and Colin Muirhead made an empirical exploration of the relative fit of these 2 forms. I'm pretty sure it was, they were then at the Radiation Protection Board, so it would have been on radiation epidemiology. And my recollection is they found something like that 80% of the time the proportional hazards was a better fit and 20% the additive form. But I think the relative insensity of the answer is for certain purposes, of course, not for all purposes. That's important. I think the last thing I wanted to comment on was this issue of non-parametric, semi-parametric, parametric. I think the way to look at it, and this isn't a theorem, but maybe a general precept, if the problem can be tackled semi-parametrically, it will usually be wise to tackle it parametrically. If the problem cannot be tackled semi-parametrically, it will be dangerous to tackle it parametrically. And the standard example of that is the competing risk model, which based on the notion that there's 2 causes of failure, two failure times, only one is observed, what can you infer? Well, under that model, so non-parametrically, anything can be fitted with those 2 times independent. Now, it's been known from before the time from the 1950s, basically. But the problem can be resolved by a parametric. So the problem cannot be, if you say there are these 2 failure times from different causes, are they correlated? And you can only observe one of them. The non-parametric version of the problem is not solvable. But if you were to say, the failure times are bivariate log normal, for example, then it can be solved. And what's being done is that any departure from the independent log normal model is being interpreted as a correlation between the underlying failure times, not as a departure from normality. So unless you had very strong reason for believing in the log normality, and in some physical problems that might be the case, but unless you had that, to think you're estimating dependence, that method is is a contric, really. Doesn't work. Well, I've written down, of course, now, those who know my beautiful handwriting will realize my notes are by now totally illegible. So I think I should end by thanking everybody today. Thank you for your kind remarks. And, well, thank you.
Thank you very much. That was, it's fascinating to see where it came from a long time before 1972, and also some reflections on the dangers of retrospection. That we shall watch out for that. I guess I do want to just offer a quick chance if there are any questions. If you're willing to just take a couple, are you willing to do that?
I'd love to listen to questions.
I suspect there may be
I've
a couple.
forgotten one piece of self-justification that I was going to make, so I might use it when in answering a question. Should there be one?
All right.
I have a very short question about the last remark you made about competing risks. The way you phrased it, would the models that Paul Lambert talked about in that context not fall into what you call the non-parametric realm?
Semi-parametric, perhaps.
Yeah, okay.
Yeah.
All right. So what's the easiest way to get?
Of course, the point in many cases is that you get almost the same answer by different methods, which is always reassuring.
Thank you very much. Quite a long time ago at a meeting, I remarked to you about how successful this proportional hazards model had been and how often I saw it in the medical papers that I read. And you made a comment, yes, but aren't they awful? And then we had to start the meeting, so I never found out what was awful about them. And I'd love to know some of the things that you thought were awful about what my medical colleagues do.
Oh, well, if there's one sin, over-elaboration. Using something, I mean, the first golden rule, surely, of applied statistics is keep it simple. But of course, not too simple, as Mozart said to the King of Leipzig. Isn't anybody going to say, what did he say to the King of Leipzig? That's what you're meant to say. Well, after the first performance of the flight from the Seraglio, the King said, very beautiful, Mozart, but too many notes. And Mozart is said to have replied, precisely as many notes as there had to be. Now, the self-justification, can I be heard? The self-justification is about martingales, a topic I'm sure dear to the heart of a tiny proportion of your audience. In my 1975 paper, martingales are used, but not used by name. I was aware that they were martingales, and that was because David Silvey, who at that time, late David Silvey, was a wonderful professor of statistics at Glasgow, he had pointed out many years before, in the 1950s, that maximum likelihood theory for dependent observations often hinged on martingales. And I knew that, but I felt, isn't it a bit pretentious to put it in the paper? Because I'm not going to really use it. And so I didn't. And maybe I should have done that. Not that I mean, it's a trivial point, really, but the message is the danger of not pointing out. One should point out connections of one's work with other things, even if perhaps they're not immediately useful. For example, one would have used the martingale central limit theorem. Well, I could no more prove the martingale central limit theorem than I could ride a motorbike.
David, could I ask you, there have been many developments of your model over the years. Is there a particular development that you're very fond of, that you particularly liked or admired or said, yes, that's very nice, I like that? I know it's a difficult question, but there may be something that appealed to you.
Well, I very much admire the Oslo work on this, and much else. And Professor Bland's comment about hating things, it must have been a bad day. But I think the comment about over-elaboration is, well, it's connected, of course, with computation. I was brought up in a time when you had some data, you looked at the data, you looked at the data again, you looked at it again, you thought, it would be nice to compute that, and you thought a bit more, and then if you really, really had to, you went and did it. Nowadays, the approach is the exact opposite of that, isn't it? It's so easy to compute certain standard things that one, even if there's no prospect of very much gain, it would almost be wrong not to do it. And that's switched the tactics of statistical analysis very drastically, mostly for the better, but not entirely for the better.
I think we'll make this the last question, because I'm pooped.
I want to ask something about predictions, Sir David Cox, and see what you think about predictions and whether actually it is logical to think that we can predict using the statistical methods that we have, predict accurately whether it's possible or not. Because most of the beautiful tools that we have are based on statistical inference, and most of it is inductive inference, which is based on the definition of probability. And probability itself, beside its abstract interpretation, has got the interpretation of relative frequency. And then at the same time, we try to use those that inductive inference to do the opposite, to predict for each individual. Is it something logical, or I don't know whether I'm being clear enough or not?
Well, you're raising profound points, I would say. And you said, of course, probabilities in the mathematics books, it's an abstract thing for, I would have thought, most of the people in this room. It's not an abstract thing. It may have, but it may have several different, the point is it may have several different meanings. In particular, of course, some notion of frequency, and there are several notions of frequency. Fisher, who one thinks of as a frequentist statistician, was very emphatic. His probabilities were not frequencies in large number proportions in large numbers of trials. There are proportions in hypothetical populations, which is something very different. Then there's probability as objective degree of belief. There's probability as personalistic degree of belief, your probability. Those are three very different things. Now, which of them is appropriate for prediction? I see the most important use of these methods we've been talking about as explanation. That if an explanatory variable is found as important, why is it important? What does this tell us about the underlying data generating process? Does it even tell us something about the scientific basis of what's going on? That's more immediately applicable, at least, than the notion, does it help us predict this particular individual? Because I don't know. If one says to somebody, if you do this, you become a member of a population, 6% of whom will die in the next year. Whereas if you do that, you're a member of a group, 5% of whom will die in the next year. I think many people, including, I think, me, would say, oh, well, interesting. I don't know if it would affect us all that much. It would have a bigger effect, yes, of course, but many, and yet the difference between 5% and 6% in terms of the population could be quite dramatic. So I think you're saying that the use of probability for predicting individual behavior is treacherous ground, and I think it is.
Well, I think such a profound question is actually a very appropriate place to end a discussion of a very profound paper. For myself, it's been a great privilege, and I guess for all of us who, for one reason or other, weren't able to be here 41 years ago, to capture something of the flavor of that. So I really mean that. Thank you to all our speakers, and of course to David for making this a very enjoyable event. There are refreshments now available downstairs, but for those who were here 41 years ago, can I repeat that plea? Could we sort of congregate at the front here and be very interested to find out who all of you were and to take a photo if that would be possible as well. So thank you all for coming. Can we